Introducing Tim Dhillon, software engineer from Blue Mesh Solutions. Over to you, Tim.
Hi, I'm Tim. I'm a C++ programmer. So I'm just going to go through a little PowerPoint. I'm just going to show you a little demo that I've done, and it consists of a Raspberry Pi, which is a publisher, and a broker, which is on my Mac, and also a subscriber, which is also on my Mac. So what will happen is the subscriber will connect to the broker, and it will subscribe to a topic, bluemesh/hash, and the hash is like a wildcard. So anything with the root topic bluemesh will come into the subscriber, and you'll see it on the screen. And then I'll plug in a Raspberry Pi, which is a publisher. That connects to a Quantrobe key management server and grabs a key, encrypts messages from a text file, and then sends them through the broker and to the subscriber. It's quite simple. This is a diagram of a flow diagram of how it works. So you can see, start the subscriber, it subscribes to Bluemesh. It authenticates with the key management server, which is hosted by Quantrobe. I then power up the Raspberry Pi. That connects to the broker. That authenticates with the key management server, requests a key, encrypts the data, publishes a payload to the broker. The broker forwards it on to the subscriber. In this demo, what I've done, for the subscriber to decrypt the payload, it needs a key ID. So for this demo, I pass the key ID in the topic. So it's a subparameter of the topic. So when it arrives on the subscriber, I parse a topic, get the key ID out, and decrypt the message. So what I'm going to do is just exit from this. So you'll see here in the blue window is the subscriber. Down here, I'm going to start a mosquito. This will show everything the broker that's coming through the broker. It will show the topic and the payload. Here I've got Raspberry Pi. I'm just going to plug it in. So you can see I don't know if you can see it. It should boot up in about 30 seconds, and you should see messages coming through. So don't forget, this is just a demo. So this isn't the actual way we will pass the key ID across from the publisher to the subscriber. I'll go through what I've done in the next step to make this more sort of production ready. And it's just a better way of implementing it. But it took quite a bit of work to change from this simple demo to actually having a proper implementation. So here we go. You can see, if we look down here in the broker, you can see the topic. Well, I'll let this run for like 10 seconds, and then I'll just switch it off. Right, so I pull that out. So everything's stopped. So we just take the first message, which is encrypted, which is this one here. The payload here is encrypted. This is the topic. In the topic, I'm passing in the key ID. This is a broker where I'm currently highlighted. Then whatever comes through this broker then gets passed on to whatever subscribed to the topic bluemesh/hash. And this is a subscriber. So it receives this message, which is the same as this one here. It grabs a key ID, which is this. It then does a decrypt function call from my API, which goes to Quantrobe. So you pass in the ciphertext and the key ID, it goes to Quadropy and it decrypts it. Here, where it's doing the this info message here, this is where I'm requesting a new key. So it's generate a new key and it starts encrypting the random messages again with a different key. I'll plug this back in. I'll just play this again. So these are some of the function calls you can call from my header file. There's only 6 functions in this header. So I've simplified the SDK from Quadropy quite a lot. And you basically just have an encrypt and decrypt function. You pass in the key ID and you pass in the text you want to encrypt. And for the decrypt, you pass in the cipher you want to decrypt. And this is how you implement it on a publisher and a subscriber. This demo, it also works with Paho Eclipse, Wolf SSL, and async MQTT5. But I'm just showing you it running on Mosquito at the moment. So we go through this code. I don't know if any of you are programmers, but so the first line is string QI space meta path. Now that is the directory where your authorization file lives. For us to get keys from the Quadropy KMS, Quadropy need to give you a authorization file for every device, otherwise it cannot connect. Underneath you have the key size in bits. It defaults to 1024. For the demo, I've set it down to 256. You then create an instance of my library with the BMS Queep call. You pass in the meta path for the authorization file and the key size in bits. You then grab a key ID. So you generate a key ID by calling generate key. That returns a key ID. And then you can start encrypting your data. So the first thing you do is encrypt your username, your password, and then you call a Mosquito call to set the username and password. Going down to the subscriber, that's just a simple call to subscribe to bluemesh /hash. That's not requiring any encryption at the moment. And then for publishing, you just do the same thing. You get your message, you encrypt it with a key ID, and then you publish with that message. In the subscriber, there's a callback called onMessage. This is where you parse a topic. So you get the topic from this Mosquito message structure. You then parse a topic to get the key ID out. And then the last line is decrypt with that key ID, the message that's arrived in that callback. So this was just a demo. And when we demoed this to potential clients, especially military clients, one of the first things they asked was, can you encrypt the topic? Which seemed to be quite an important thing for them. So I went back and worked out a way of encrypting the topic. This required modifying the Mosquito open source broker code. So you could pass a key ID into Mosquito rather than just passing it in the topic, and which is sort of a messy way of doing it. So this is the extended API for Mosquito. If you look at the bottom functions with the Queep on the end, those are the ones we've added.
You might need to highlight that, Tim. It's a bit small, a bit on the tiny side. Well,
Oh, this is on the PowerPoint, so it's not in my. I can bring up the code
oh yeah.
in actual.
Or if it's PowerPoint, you could just highlight it.
It's not. It's keynotes.
Right.
And I'm not 100% right. Here we go. So these are all the Mosquito functions for each version.
Oh yeah, that's better.
So here we go. So these functions are my functions, and the same as the Mosquito functions, except they take one extra parameter at the end, which is a key ID. Can you see that? So modify the Mosquito message structure, and the last parameter after the return, I've added a key ID. So the key ID is passed from the publisher all the way through to the subscriber. And so this is how it looks like now. So the subscriber initializes, connects to the broker. It authenticates itself with the Quantropy KMS, and then it requests a key. We then encrypt the topic with the key, and we subscribe to the broker with the Mosquito subscribe underscore queep function, and that encrypts the topic. When it arrives at the broker, just before it enters the broker's routing table, it just decrypts it at that point. And then on the publisher, it does initialization, connects to the broker, goes through the same process, authenticates with the Quantropy KMS, requests a key, encrypts the payload and the topic with the key, and it publishes via the Mosquito message queep function, which passes in the key ID. That goes to the broker. Just before it accesses the routing table, it decrypts the topic, matches whatever subscribers need to be, the message needs to be passed through to, and then it encrypts the topic again, and that's forwarded to whatever subscribers have subscribed to that message. It then grabs the key from that Mosquito message structure, the key ID, so it decrypts and decrypts a message, the payload. Okay. So the new code which you add to your publisher and subscribe would look like this now. It's very similar. You get a key ID, call the generate key. You call the same encrypt and encrypt functions, except on the username password set, you call the set queep. And the last call, the last function parameter is a key ID. Same for the subscriber. Instead of calling Mosquito subscribe, you call Mosquito subscribe queep and pass in the key ID. Same for the publisher, you just pass in the queep and the key ID. And then on the callback at the bottom in the subscriber, you just get the key ID from the Mosquito message structure. So you don't need to parse any topic to get the key ID. And then you just decrypt. So to modify the Mosquito code, I had to write a C wrapper because Mosquito's in C and not C.
It's now perhaps a good time just to go through the questions before we talk about how you modified this code.
Yeah,
Richard, Tim?
Yes, yeah, okay. So the first question we received was from David, and his question is this a normal flow for device MQTT, meaning to have the device do the payload encryption rather than using, say, TLS, for example? And what we're trying to describe here is double wrapping the payload. So the device can still use traditional whatever normal, I don't know what the word is that I'm looking for there, transport layer. But prior to the transport layer being engaged, and it doesn't have to be TLS, it could be Bluetooth, for example, or any other communication framework, really. This also works on UHF radio waves. We take the payload and then we wrap it with this method that Tim's using, which is called KEEP, which is a symmetric quantum key exchange, and it allows us to add a 1024 expanded permutation space onto the key length, or the key space, which is if you think AES runs on 256 and we're using 1024, it's many times greater as a permutation space. So yeah, we are undertaking the payload encryption once, delivering it on whatever standardized transport layer is being used, and then unpacking it at the other end, as Tim was just describing. So it's a way of wrapping up the payload and giving it a much higher level of encryption. The payload itself, using this keep method, also takes a key seed, so the actual seed for the algorithm, and it takes that from an entropy source. So we have a entropy farm where we generate QRNG, or entropy, and then that entropy string is used to seed the algorithm as well. So you've got another hardening boost there as well.
Yeah. On top of that, the broker data that passes through any broker is using TLS. As soon as the payload and the topic reach the broker on layer, I think there's layer 4 where TLS works, then everything becomes plain text. So the broker can see the header and do its work. Doing it this way, the payload is encrypted. The payload is still encrypted on the broker, so it never gets decrypted. It only gets decrypted at the subscriber. So if the broker is compromised in any way by a bad actor, a bad admin, or someone's managed to get in there, then they can see, if they just do a mosquito sub, like I've done on that window, mosquito sub -T and then a hash, which is a wildcard for everything, they'll be able to see everything coming through on the broker in plain text if you just use TLS. With this Queep method, everything coming through will still be encrypted on the broker. The other reason this method is good is for constrained devices, 8-bit, 16-bit controllers, where the TLS handshake takes up quite a bit of memory, and this is good for constrained devices as well. So it's good for constrained devices where TLS can't be used, but also it's good to use for normal devices on top of TLS. So it gives extra security.
Yeah, that point about speed, Tim, you just made. I've actually got a bit of text in front of me here, and it says that this method that you're using or calling performs 18 times faster than AES 256. So it's more lightweight with its code footprint.
Yeah, and just because a constrained device can handle a TLS exchange that uses AES and RSA doesn't mean that you'd be able to load all the post-quantum crypto on top of that and it still fits. It may well be that you're bumping up against the upper limit as it is today, and then the extra load of the post-quantum ciphers would just not be feasible. So this mechanism lets you offload the post-quantum crypto onto the Quantropy servers.
Yeah. Great point. Okay, so Charles asked No such thing as a dumb question, Charles. He said, dumb question. Can you talk a little bit about how the actual quantum encryption piece operates? So, yeah, so the architecture, Charles, is that Tim, you pick up if I'm too high level here. The architecture is that back in the mothership, if you like, in the cloud, there is a quantum entropy farm, and it's called a farm because we use different devices to create quantum entropy. There's about 4 or 5 different suppliers in the market, so we just basically put them all into a server farm, mix up the results, and then use that as the source. The QRNG, the quantum random number generation strings, as hex strings, are then delivered as a SAS, if you like. You can have them as a SAS resource, or you can have them. You potentially can have them on-prem as well, so you can have your own on-prem source if you want to be super secure. The QRNG and the key material and the key requests are then managed by your own management node. That manages the key requests from the devices and the key requests from the other end that needs to pair up again on this symmetric key method. The encryptography that's used, as I said, it uses as a baseline 1024 as the permutation space for the encryption. And that can be expanded all the way up to 32,000 bits. So you can set it in a kind of crypto agile way to respond to whatever whatever memory space or threat you feel is appropriate. The connection between the devices is managed by the management layer. So Alice as one end point, requests to speak to Bob as the other endpoint, and then the keep algorithm manages the Alice and Bob negotiation by negotiating back to the management panel or the management node. So that's how the quantum encryption piece operates. Tim, do you want to add to that at all? I don't know if I've
no, that's
done it justice. Is that okay?
Yeah, that's good.
Thank you. Yeah, it makes sense. I guess as someone who doesn't know much about encryption, and listening to some of the comments, that the question, the uniqueness here is how do you bring the whole system together around that? I suppose, given the uniqueness of the quantum farm and so on as you described, and I suppose also if you've got this super secure capability, how do you build that across the whole system architecture so you don't drop the ball somewhere?
You can air gap this as well, Charles, and in military use cases, this is currently being used in a fully air gapped setting as well.
Yeah, I was kind of thinking about that, and the question earlier about encrypting the topic, because if it's no good having incredibly uncrackable encryption in the specific data you're transporting if there's some loophole somewhere else in the overall system.
Yeah, we showed it to Hive actually a few months ago, and they came back to Tim and said, "Can you work out how to encrypt the topic? Because that would be really useful." And that's why Tim then went away for another few weeks and worked that one out, didn't you, Tim?
It was more than a few weeks.
Yeah, thank you. No, yeah, good explanation.
David has asked, is that a Pi 5? Now, I guessed it's a Pi 4, isn't it? But that was my guess. Is it a Pi 4 or Pi 5?
Let me look at it. It's a Pi 5.
Oh, I got it wrong. Okay. But David's real question was, would it work on a less powerful device such as a Pi Pico? Now, I don't think we've tested on Pi Pico, have we? We've tested on the other one, haven't we? The one in the middle. What's that called?
We've done Pi Zeros.
Pi Zeros, yeah, of course.
For demo purposes, we realise that when we take these off-site or to clients, connecting to a hotspot, the Wi-Fi signal needed to be stronger. So we went from Pi Zeros back to Pi 5s, just so the just 'cause they seem more reliable. And just getting a demo to work generally is not always. It doesn't always work when we turn up there, but using these Pi 5s, it's always worked.
Yeah.
It was more a question of whether the algorithm was something that could be scaled to a very small device, or whether it needs the power of Pi 5.
No, I know that it runs currently on NRF 52840, which is Nordic Semiconductor Bluetooth module. And that, if you dig away through the layers, you end up with an ARM Cortex on there.
I think it's an M33, I think, isn't it, that one?
Yeah, I guess so. You know the numbers. So I know it runs on that. I know it's running on an ST Micro kind of will do anything platform, and it's also running on Renesas as well at the moment. Now, I said, I also said below that I know that ARM are currently doing some work on creating something called ARM Vault in the memory. And ARM Vault is a secure area where you want to put your identity and your certificates, etc. And this solution as well is being packed into it at the moment. And I believe we'll be able to tell you about that work quite soon. ARM Vault, as you might know, I don't know if anybody knows about it, it creates a kind of a safe locked away space on the device, so that if you're a bad actor or bad administrator or whatever, you're not leaking parts of the memory out that then can be side channel attacked. Well, that I'll bring you some more news on that quite soon after Embedded World. Sorry, I'm lost. Anupam, can the decryption happen locally at the subscriber?
Yeah, well, that's what was happening. We go back to. So this last function call, the void on message, that's in your subscriber. That's a callback. So whenever the subscriber receives a new message, it comes into this function, and this is where you just do your decrypt.
Okay, so I think in that diagram, it sort of seemed to me that it was sort of sending the encrypted message and the key to the Quantropy KMS, and then that was doing the decryption. So it's
this diagram or the diagram before.
I think the diagram after. So once it gets the message which is encrypted, it sends that, and the key, it sends it to the Quantropy KMS, right? For decryption. That's what I remember saying. But
yeah, so the key the key ID is the key to this. Pardon pun. Once a key ID is received by the subscriber from the publisher, you can then go to the KMS and get the actual key. But the key is never shown. You basically call a decrypt function, and inside that decrypt function, you pass in the key ID and the cipher you want to decrypt, and that function goes away and under the hood gets the key from the KMS and does a decryption and returns you the decrypted message.
and where does that function gets executed? Like at the Quantropy KMS servers or at the subscriber?
That's inside my library in the Bluemesh lib.
Okay, so that will be part of the Quantropy KMS, right?
No, the Quantropy KMS contains the SDK. Yeah, well, yeah, it will be passed inside the Quantropy KMS.
Okay.
It's a function call on the KMS. If you see what I mean? It's not inside the KMS.
Okay. Okay, like a callback.
Yeah.
Okay. Yeah, I was just wondering because if the subscriber has the key and the payload, it should be, I mean, it can just, yeah, because the issue was then the Quantropy KMS sends back the decrypted payload, and that can be sniffed as well, right? So
No,
because
it's not. It's not sending back. It's sending back the key, but the key's encrypted when it's sent back from Quantropy. So when it lands back on your subscriber device, inside my API, my library, that's when it does the decryption.
okay.
Yeah, that's the operation that happens in the secure enclave, like the ARM trust zone or some other equivalent, where the encrypted key gets passed in and the crypto information is in some sort of siphoned off bit of RAM that the CPU works on, and therefore, if your operating system or anything higher up the stack is compromised, then it doesn't get access to the keys.
Okay.
What's used to encrypt the key as it comes back from Quantropy to you?
Sorry, what's used to encrypt the key?
So the key that comes back is presumably encrypted, not plain text.
Yeah.
And so what key is used to encrypt that key? And is that what kind of crypto is used on that transaction?
Right. So Quantropy have got their own encryption methodology, and the key that's used to decrypt that inside the Quantropy SDK is something we would have to speak with Quantropy about. I'm not sure.
Obscure at the moment.
Yeah.
Yeah, but it's swappable. So if you wanted to use one of the NIST set, for example, and it would run on the device, then you could swap that in as an alternative.
Yeah, you can use a different crypto library.
Yeah. Okay.
So I think I've done this demo before with the Crypto++ library, and I've done it. I've written this in Python as well with is it Fermat or Fernat library that comes with Python. So there's different ones you can plug in and out.
Yeah, and actually the Quantropy library is actually a derivative, a fork of libQoS as well, which was originally IBM, I believe.
Yeah, but I think there's when as an enterprise you set this type of thing up, you'll have some sort of privileged server from Quantropy maybe, and then you have a privileged connection back to the Quantropy server, and that handles the key exchange in the background somehow. But yeah, this is hand wavy because we don't know the exact details of how that's typically deployed. But yeah, they have a manual that we can share. Or perhaps they can talk about it in the next SIG. Hint the future.
So for the purposes of this demo, that is that's sort of outside the scope of the demo. The demo is about the middle bit where the symmetric stuff happens.
Yeah, let's call it out of band for this.
Yeah, okay. And the symmetric stuff is also something that they've created. They've created this funky beyond AES or something. Why?
The symmetric MQTT, we actually asked them to produce it for us in their SDK, so it wasn't actually in there. So we went through and suggested our requirements for them to give a solution so we could have symmetric keys through MQTT. So we worked with Quantropy, they modified their SDK, and we've ended up with this solution.
Yeah, but I think that is true, Tim. But I think maybe to answer your question, Martin, on a different level, Quantropy had already developed their own post-quantum symmetric cipher called Keep that they were using for some military use cases. And then from our discussions with some of our customers at Bluemesh, it became clear they were interested in having a post-quantum symmetric cipher in the solution we were proposing to them. So we asked Quantropy to join the dots there and expose their symmetric key through this infrastructure. It wasn't the case that we came up with a requirement and then they built a post-quantum symmetric cipher for us. Right, that was already on the shelf because of some much deeper work they've been doing with defense in North America.
But what do they know that I don't? I thought AES 256 was fine.
I think it's fine until it's not, and so there's possibly a couple of answers to that. The first one is that it's fine until it's not. Second one is that for some of the more restricted IoT devices, then to get a higher level of encryption to quantum safe standards using a different approach than trying to put some of the larger NIST PQCs onto the device is the approach that Quantropi are taking.
But that's my point, though. AES 256 is available all over the place and is quantum safe as far as I'm aware.
Yeah, 100%. The advice from NIST and then CSC to the general market is that AES is solid. You just need to focus on RSA and the other asymmetric ciphers that are susceptible to Shor's algorithm. But I think they have other clients who are more paranoid than is expected for the general population, because it's always a cost-benefit analysis in these things, right? Trying to get everybody in the world to move off RSA to something that's going to be quantum safe is a hell of a job. Adding symmetric on at the same time when you think probably all right, like let's focus on the thing we know is going to be bad and make sure you're not that off. But then if you're in certain spooky circles and you just want to make sure everything's going to be secure to a mega paranoid level, and you've got the resources to make that happen, then they do what they do, right?
Yeah.
I think that's how I squared it in my mind anyway.
Right. So for the purposes of this demo, again, we could replace that with AES 256 and it would still be a quantum safe demo from the point of view of normal people. For me as a purveyor of IoT devices, I could take this scheme of working, use AES 256 and still be fine. According to the guidance from NCSC and co. I'm not asking you to put your neck on the line. I'm just
the weak spot that's discussed in AES is the initial handshake, which is still using public-private key exchange on RSA on a lot of.
But as we've discussed, that's not part of this demo, and we don't know what that is in this case. We could go down a different rabbit hole there. Anyway, I've talked too much. Someone else can have a go.
We're post RSA handshake. That's what we are. So that's Martin. We've dealt with that. And I've got Newbold here. Would this demo be the same pre-quantum? And therefore, the part that's making this quantum secure is that the KMS holds post-quantum algorithms. Okay, I'll go first then. So element one, the seed in the algorithm is from a QRNG source, an entropy source. So that's one difference. And the KMS holds post-quantum algorithms. Yes, it holds algorithms that are either based on the standard NIST set, or there's other Quantropi algorithms which basically achieve a very, very similar outcome, very, very difficult to reverse engineer, very high permutation, very expanded permutation space, which basically makes them quantum secure. We have to put a word of warning here that the algorithms used in conjunction with a standard, so let's say AES, will pass certification tests. Used alone currently, they won't, because they're not NIST approved. And and I know that the whole set is being prepared for NIST approval at some time in the future as well. So just saying that out loud. Steve?
Yeah.
Yeah.
Agree.
Okay. Mike. Mike says, so on the basis that each device gets a cryptographic identity, usually a key pair or certificate, a token, I think they say in the Contropy language. So I'm a building controls technician and need to replace a piece of hardware, let's say a sensor. So I bring along a replacement to physically replace the broken one. What actions are needed to make this a seamless process? Okay. So the gateway, and Tim might chip in here, but the gateway, the broker that you're going to use will need to be Quantropy enabled, and the RTOS, or maybe it's just an operating system, I don't know, on the device that you're trying to swap out will need to have the same Quantropy stack on there, so that they can collect their QRNG and undertake this symmetric expanded protection of the payload. So you'll have to have the broker, as Tim's designed here, would have to have the Quantropy enablement, and so would the RTOS, the sensor device.
Maybe the broker will definitely need to be changed. The device, you could just install the library and modify the code at the publishing when you do the publishing. You just add in the two function calls.
Oh, that's true. Yeah, you wouldn't need to rip and replace. You could just update. Yeah, fair enough.
Yeah, you just have to link in the library to your code and add in 2 calls, or 1 call even.
Yeah. Okay. So Newbold has asked, I assume this is using MQTT over TCP, which it is. Has it also been tried with CoAP and UDP? I think we've just done it on TCP/IP, haven't we, Tim?
Yeah, just TCP/IP at the moment.
Yeah.
Do we know of any reason why it wouldn't work on UDP?
I don't see why not.
Yeah, that's not quite true, actually. We've done it on Bluetooth as well, without TCP/IP on it. So it does translate onto different communication frameworks. Okay, Ranga does, with Keep being a proprietary scheme, will this solution be certifiable by standards bodies, FIPS, etc.? Kind of touched on that, but I'll go back over it. No, not in its raw sense. But if you double wrap and transport on a FIPS approved transport algorithm method, then yes. And as Tim pointed out, wrapping to 1024 or higher, passing that then to the transport layer, delivering it to the transport layer across the IP, unpacking it on the port, still encrypted, and then delivering it to the application layer is much more secure if you've got people sneaking around listening to your TCP/IP ports. Super. Okay.
Just on that question as well, I think you'll learn more about it in the next SIG in April. But Quantropy are working with one of the contractors that NIST use for certification of ciphers, a company called CoreSec Security, CORSEC. So they're in the queue. But if you remember what Ben said last time in the SIG, FIPS has been NIST have been impacted by the US government shutdowns and things. There's delayed Falcon being published. So things are a little bit slower on their end in terms of getting certifications, I think, than has been traditional. And I think they've generally been quite slow as well. So double slowdown.
As the as these software tools or the software library has been designed for very much for IoT, very much for constrained devices, as there's work taking place with ARM with this SDK, and as like I said, Renesys and ST Micro have both adopted it, made it an option for some of their platforms. I'm going to try and get the CTO on for the next SIG, and we can really deep dive into all of these technical questions, and hopefully everyone will join us for that question and answer session. Today we threatened you with some code, which we've delivered on. Well done, Tim. Thank you very much. We also threatened that we'd wave a few Raspberry Pis around, which Tim also did. So we've delivered on those points. I hope everybody enjoyed the session, and we'll see you on the next SIG, where we can deep dive even further, hopefully, into these technologies. Thank you very much.